Okay, let's get going then. So Docker is still somewhat popular. I think I'm a couple of years behind the hype curve. So this talk is going to be about lessons learned, things I've had to learn to effectively use Docker in a production-like environment over the last year. It's not going to be any introductory material to Docker, so my assumption is you know what it is, you've used it probably, you know the CLI. It's going to be about how to diagnose problems in JVMs when they're running inside containers. So hopefully that's what you're expecting. So the way I'm going to do that is first talk a bit about the motivation for actually using Linux containers to deploy our Java applications. My hope is that you have a very good reason to move to Docker, and it's not just because someone told you to do it at a conference. The reason I want to talk about the motivation for a couple of minutes is I might be somewhat negative / put you off trying to do it, but I wanted to make sure I do reiterate that I do think it's a good idea as long as you've got a certain set of requirements. As soon as we've got that out the way, what I want to do is talk a bit about how Docker containers work. And I'm going to talk about a couple of Linux features called control groups and namespaces. And the great thing about learning that stuff is it's applicable even if you decide to not use Docker for the rest of your life. It's applicable if you decide to use Rocker or you decide to use cgroups directly or using something like systemd as your init system. And I'm going to do that by example. So online, I've got a couple of example Docker images which I'm going to play with and hit with some load and show you how they behave when they're inside a container, and then you can go and play with that yourself. The idea was this could be a workshop. So anytime I show you I say this container X is running, you can go and grab that container. There's a little Gradle project which will build them all, and then a set of Docker Compose files which will start up Docker containers with various configuration options. I'm not going to talk at all about Docker Compose. If you don't know what that is, I don't care. But just know it's a YAML file, which means I can boot up a bunch of containers and you can recreate what I've done on the screen here. So the example I'm going to do is I'm going to have 3 separate containers. One of them is going to contain a JVM which has a Ratpack application in. Anyone use Ratpack here? So Ratpack is a non-blocking framework for building web applications. And the reason I've got one of those is I find that JVM behaves very differently, and you have to configure it differently if you're running a non-blocking application versus a typical synchronous application. And by that I mean something like Jetty or Tomcat or any kind of application server that you're used to using, where a single user request or automated request comes into your system, and that request gets a thread for the duration. So I do think those kind of things behave a little bit differently. To add some sense of realism to it, both of those do the same thing, and they make a call out over HTTP to another container, and all that will do is echo the response. But it's just so we can see how things behave when they have to make external calls out. All of the screenshots I'm going to show you and demos were on my desktop, which contains 12 cores and 64 gigabytes of RAM. Even though you're probably told I run Docker on my laptop, it runs the same in production. That isn't the case in my experience, so this will become very relevant when we're looking at examples down the line. And just to generate some load so that the applications under test will actually have something going through them, I just used Apache Benchmark, which just is an easy way of generating some HTTP load, but that's not really important. So before we jump into the technical stuff, I want to talk a bit about motivation for actually running our JVMs inside containers. I've gone through a whole cycle in the last 10 years of deploying Java applications differently. I used to work on typical deploying WAR files to application servers. I assume a lot of people still do that today. And even though that could be frowned upon at the conference scene, it really did offer us a nice abstraction. We deployed a WAR file and someone else managed the infrastructure. If the host changed under the covers, we wouldn't actually know, right? They would require a restart or some description, but we weren't coupled to a particular piece of hardware. Certainly in the last 5 years, I've seen a lot less of that, and I've been building a lot of applications which have like embedded web servers. So they've got an embedded Jetty or an embedded Tomcat, typically building an executable jar with something like Spring Boot, which you may have just seen a talk on. In my examples, I'm using Drop Wizard, which is very similar. And the great thing about that is it's fully self-contained. The only dependency of an executable jar, which embeds a web container, is a JRE. So are we seeing a lot of benefits by packaging a Java application inside a Docker image? I don't know. Who knows? But this has a real problem when we do this. And if you've got a lot of applications running, and you've got a lot of test environments, and you've got your functional test environment and some integration environment, and then you want to spin up another version of your application because another team wants to do some integration testing with you, I find this becomes a pain, even if you've got really good infrastructure as a service, either by like a public cloud provider like AWS, or you are running your own kind of private cloud with something like CloudStack. It's still quite a lead time to boot up a new application. You still need to, say, write some Puppet or some Ansible, etc., which provisions those hosts. And the feedback time for bootstrapping a new team or a new component could still be half a day, which does tend to take a long time. However, the main reason I don't like this model is it becomes far too expensive. If you've got lots and lots of test environments, and even if you shut them down at night, the hosts involved there will be heavily underutilized. Unless you happen to have this perfect hardware aligned with the load coming into your application, and that load is constant, but typically your load is very spiky. You might have a busy period at the end of the day or at the start of the day. So virtually every time I've deployed applications in this model, you've wasted a huge amount of resources on that hardware. Who here runs inside AWS? Lots of people. Wow, that's more than last time I asked that question. Well, AWS offer you a really cool tool. It's called, what's it called? I've forgotten. Trusted Advisor. And this actually is a tool built by Amazon to tell you how to give Amazon less money. I don't get why they do that, but they do. And this is an account from a few years ago, which I used to work in. And what it'll actually tell you is how much money you could save a month. And in this one, it's $106,000 a month. Just think who you could hire. Think how many meals you could go on. This is a lot of wasted money. And Trusted Advisor will even tell you why you're wasting all of that money. In this case, it was nearly all low utilization EC2 instances. So we had virtual machines which had a very low CPU percentage, even though we'd used really small ones and shut them off at night. So we definitely need a way, in my opinion, unless you don't have many JVMs, to have multi-tenancy, to basically bin pack them all in and have as much utilization as possible, because it's just a good return on investment. But running multiple JVMs on the same machine is challenging, right? And a lot of the problems you're going to have with running JVMs inside containers, you'd have very similar problems if you just run loads of JVMs on the same host. I used to do a lot of work with Apache Cassandra and Apache Spark, and when you put them on the same host, boy, do they want to fight for all of the resources. And that's going to happen if you decide to deploy multiple JVMs to the same host. There's something awesome about the JVM is most of the time it doesn't need a huge amount of configuration. Normally you might play around with garbage collection, etc. But unless you're in a low latency space or you're really trying to tune things, you can get away with probably less than 5 options or 10 options. And there's a reason for that, right? The JVM does not pick defaults, does not pick hard-coded defaults. It bases it off the resources of that host. It's going to pick the heap, assuming you're a 64-bit Linux. It's going to pick the heap, a quarter of the available RAM. It's going to pick an appropriate number of garbage collection threads. And that's just the JVM. So if we do make decisions like how many garbage collection threads should we have based off the host, and then we run lots and lots of JVMs on the same host, then we're going to have far too many threads, we're going to have far too much contention, and things aren't going to go very well. So that's basically my only reason why I would ever use Docker. I want to stick more things on the same host. That's mainly in production. I use it a lot on my laptop to boot up dependencies and in CI, etc. But for actually going to production, unless you want to run many JVMs on the same host, I really wouldn't bother. But if you do want to do that, I think Linux containers and Docker is the most mature kind of easily usable tool for using them. Then it's a good choice. But soon the fanfare and the hype is going to go down, and you're just going to end up with lots of JVMs and Docker containers running in production, and then they're all going to behave terribly and die at some point. Well, that's what I found. So to understand why that happens, we do need to understand a little bit about what a Docker container is. And what I want to do is have a look at a couple of Linux features. One of them is namespaces. The other are control groups. We're going to spend most of the time on control groups. This is a thing which allow you to slice up resources and get metrics about resources of a host and give them to groups of processes. So you can say, these 6 processes, they get half the RAM. These 2 processes get the other half of the RAM. And that's what Docker's using under the covers. But you have to really make sure that the processes actually are aware that they're not getting to use the whole host. Because most processes will try and use as much memory as they can or they need to, if you don't tell them otherwise. And I'm hoping to do that by showing you some examples. So I now use a lot of tools when trying to work out why on earth my Java application isn't working particularly well that I didn't use a couple of years ago. If you're a real Linux nerd and performance nerd, you probably just use them all already, but I certainly had to learn a lot over the last year. So here's a list of some of them which we're going to go through today. So if you're in Daniel Bryant and Steve Poole's talk before, they made the really good point that a lot of tools that we're used to using day-to-day basis, a lot of them are not namespace and, well, not cgroup aware. So you run them, etc., and they're not giving you a view of just your container. Sometimes we like to see Docker containers as lightweight virtual machines. So we Docker exec into it, and we feel like, oh, I've kind of like SSH'd in. And then I run a command, and of course, I can see the entire host resources. So it's kind of like a leaky abstraction. It's better to actually understand what Linux containers really are rather than trying to liken them to virtual machines. So we're going to go through how we would use normal tools, which we've probably been using for years. Then I'm going to jump on to a bunch of tools which are actually control group aware. So rather than having to chase around and trying to work out what's going inside top, there's something called cgroup top, which will show you how much resources each of the control groups are using. And then we've got things like DStat, cAdvisor, which I'll show you as and when we get to them. So to give you some context, all of the containers which we're going to be running and then hitting with some load, they've all got this common base image, which isn't particularly exciting. It uses the Fusion base image, which you haven't come across before. You should go and read it. It is a really good base image for solving the PID1 problem and zombie processes, etc. If you don't care about that stuff, just read it anyway, and you'll care about it by the end. All it really does is download Java and stick my favorite start JavaScript on the path. And then each of the child containers, the child images, they'll just use that script to kick off a JVM. So here's one, for example, which is the Ratpack application. This will all be built with Gradle if you want to play with this. It'll essentially add an executable jar into the container, then call start Java and say, run Java -jar. So let's start off. So I'm guessing most people have done this. So they've Docker exec'd into a container. Has anyone not done this? This is fun. No? So essentially what this is doing is when we kick off a container inside Docker, it's created a bunch of namespaces which are a way to isolate resources like network or the file, your own mounts. And it's created some control groups which are what the operating system is going to use to make sure those processes don't use too much memory or too much CPU. What we're actually doing when we do the Docker exec -it, container ID, and then bash, is we're running the bash executable inside that container. So if you've got a really big problem and you decide to do this and you run some command which is then going to use a lot of memory, maybe you're doing a sort or you're grepping some really big log files or you're doing something, anything you kick off from this bash process is inside that control group. So I often see people, they jump into the container, they run some command, and they kill all of the processes because they've actually just used up all the allocated resources by kicking stuff off from bash here. So I do my very best to never ever do this and try and use tools on the host operating system to try and outwork what's going on. But we're going to do it sometimes. And we've run the ps command, which is just going to list processes. And this is a good example of how the process namespace works. We don't get to see all of the processes that are running on the host operating system. We only get to see about 11 or 12, and most of those are started by the Fusion base image. But third from bottom there, we've got our Java process. We've got Java -XX, native memory tracking, unlocked diagnostic options. So we can see that it's just a normal process. But if we jump out of the container, or we come out of that shell, and we run ps just from the host operating system, we also get to see those processes. So this is where that whole trying to describe a Docker container as a lightweight VM has just gone out of the window, because they are just processes running on the host operating system. And if you can't see it there because it's flat, we can see our Java process is process 29895. Once you know what your Java process is running inside a container, you can just go back to the same way that you would normally try and, debug and diagnose like performance problems with your Java application. So we could jump into htop, which is like top but really colorful. And because I'm hitting that Java process, I think this one is the drop wizard application with Apache benchmark, you can see it's right at the top there, 29895. Even though it had PID 12 or so inside the container, from the host operating system, we can still see it. We can still see that it's using most of the resources. And then third down, AB, that's the Apache benchmark tool. That's obviously using some CPU to generate the load. Of course, we can use top as well if we prefer that. And again, it's much clearer on a screen actually because it's black and white. But 29895, it's up to 183% CPU there. Slightly more than before because obviously Apache benchmark's having more fun with it. But we can see that Java process and we can just start to diagnose problems from there. So we don't generally need to run top and htop, etc. inside our containers using the whole Docker exec trick. We can just run them from the host operating system. This kind of works until you've got 100 different Docker containers running on the same host, all running JVMs, and you're like, which is which? I have no idea. Whereas I'm sure a lot of people have done Docker PS and you can see you're running containers. And it gives you that nice don't want to do that. Sorry about this. Where were we? There. So when you're in Docker PS, it's going to give you a list of the running containers. And it gives you this big ID, right? You've got this 1F8D1, and that ID is then used in the operating system as the name of the control groups that Docker creates. So once we've done a Docker PS and we memorize these lovely hashes, then we can use a really cool tool called cgroups, and unsurprisingly, that lists the processes that are running inside each of the control groups. So cgroups will see we've got a parent of Docker, and the Docker PS output truncates it, but we can see just under Docker, that same ID, that 1F8D18, we can see all of the processes that run under it. And right at the bottom there is our favorite process, 29895, which is our JVM running inside our Docker container. So that's the default way I would try and dig out which processes are for which container if I'm trying to work out what's going on. Another thing is, sometimes you won't have this tool installed, or maybe you don't like this tool. You just like looking at file systems. So all of the information which cgroup top is using and all the information about cgroups on Linux is generally stored in the file system. And on Fedora, certainly, and on CentOS, we can look inside /sys/fs cgroup and then memory docker, and we can dig in there, and the same ID becomes a directory name, and under there are the process IDs. So even if you don't have cgroups installed, just remember I can actually go and look actually in the file system and work out which process is from which container. This really helped me at one point because sometimes Docker doesn't do a great job at validating your input parameters, and you get some really cool error messages out of it. Until I knew roughly how cgroups were implemented and how the data for them was stored, I would not have had a clue what this error message meant. So I can't start the container system error write, and it's trying to write something. But that's because a lot of the parameters you just pass into Docker are directly just passed into cgroups. And then cgroups will say, that is a ridiculous argument for your CF, for your quota. And at least then I know, all right, I'm just going to go and look at the man pages for control groups, and it will tell me why I've specified a stupid parameter. The Red Hat docs are absolutely immense. Like, whoever wrote them at Red Hat, love you. Because they'll explain control groups in like immense detail. And regardless of if you're thinking about using Docker in production, I would just read through these docs. And it's going to be knowledge which is going to be relevant for you regardless of if you use Docker or not, because lots of things you use control groups under the covers. So you can get some transferable knowledge there. So let's go into some specific examples about limiting CPU and limiting memory inside Docker, which is really just limiting it inside control groups, and then see what happens to our poor JVMs. So I'm going to start with memory. So if you want to override the amount of memory a container uses, it's quite simple. When we run it, we just pass in -- memory and we give it a value. What that's going to do is it's going to affect the parameter which goes into the control group which our processes are running in. Now, one thing that's interesting to note is if you jump inside the container again with bash, and then you do free -m, which is just going to give us the free amount of memory in megabytes, the first thing you'll notice is that most operating system tools are not cgroup aware. So this is just going to read /proc/meminfo, and it's going to give us 64 gigabytes. So that's your first smell that this JVM might not run very well with 128 megabytes of control group memory, but then it might try and use vastly more. So one of my sneaky Java options inside my start JavaScript is to set the min and the max heap to the same, and to set it to 256 megabytes. That seems weird because we're giving the container 128 megabytes. Who would like to guess what happens when you run Docker run with this? Shout out a guess.
OS level of memory?
Yeah, so this container is going to get killed, and Docker may or may not tell you that that has happened. So one of my favorite tools when I started running JVMs inside containers was just to always look inside dmessage whenever my Java applications vanished. So unsurprisingly, if we try and start up a JVM inside a Docker container, and it tries to allocate more heap than we've given memory to that container, then, yep, the kernel's going to come in, and it's basically going to see memory cgroup out of memory, and it's just going to kill it. No graceful shutdown, it's just going to get karate chopped. Okay, so what do? We give it some more memory. Who thinks that this is going to survive? You have to put your hand up one or the other. Who thinks it's not going to survive? Who thinks it's going to survive? Okay, it does survive, right? Almost surprisingly, because we all know that heap is only a very small portion of the memory that a JVM uses. There's a slight caveat to that, though. It was horrifically slow. Surely it would just die, or it wouldn't die. So I was like, what's going on? So we've got our container running. Evidently, I went for a cup of tea because it's been running for 5 minutes before I decided to work out what was going on. So we've been running for 5 minutes. It's running horrifically slowly. The throughput was less than a half from Apache benchmark than before when I just gave it unlimited memory. Another really cool tool is cgroup top. So again, you might not have this installed on whatever operating system you're using, but essentially it's reading that data on the file system in sysfs cgroup, and it's giving you a CPU usage at the container level, so the cgroup level. So again, you have to run docker ps to work out which one is which, and we can see that our control group there is using 12 processes, CPU percentage 356, it's really going at it now, but it's using 298.9 megabytes of memory, which sounds about right. We gave it 300 megabytes of memory. So what's going on? This is my second favorite tool. A really cool guy called Al Toby got me into DStat. It is basically every Linux tool you ever want all munged into one and made super colorful. So like it's IOStat, VMstat, it's uptime, it's like all of them. And you know, if you do /lv, V is for VMstat, and then etc. But if we have a look at some of these numbers, I kicked this off, and this is giving us numbers every 10 seconds. And I kicked it off before I started. So the load average onside this computer, it's like 0.3, 0.2. That's at the very far left. And then I start the Apache benchmark in the container, and then it gets bigger and bigger and bigger. And you have to believe me if you can't see in the middle. It gets to around, you know, a load average of 6-ish. Another interesting thing I like, the memory usage. You can instantly see that this has a used memory of 10 gigabytes. It has free memory of the column roughly in the middle of 45 gigabytes. It gives you things like you can do context switches and interrupts. You can see right at the start there, they're just under system. And we started off with interrupts and context switches in the single-digit thousands, like 2,000, 7,000. We kicked off our good old drop wizard application and Apache benchmark, and then we got into the hundreds of thousands of context switches. But that's not the big, horrible thing in this diagram. The big, horrible thing in this diagram is the paging. So this is basically some of the memory that this process is using is actually living on disk, and it's been paged in and out of it, which is quite bizarre given that we've got 45 gigabytes of free memory. And if we looked closely at cgroup top, that would have actually told us as well. So on the far right of the column is actually the I/O. So unless your container is reading and writing to disk, this should really be 0. So what was actually happening was that even though the operating system did not need swap, the container was being forced to use swap because we'd limited its actual memory, which was interesting. even though most servers these days have swap disabled anyway. But we could have also seen this inside htop. This is pretty much always 0 on this machine, but it was 174 megabytes. So that kind of implies that I was using up my 300 megabytes of actually like resident memory, and then another 180-ish megabytes of memory, which was in swap. So to disable this, so this doesn't happen, because if you're deploying lots of instances of your application, a slow one is normally vastly worse than a dead one, because you'll either recreate it, you'll change the parameters, etc. So for me, I don't want a slow application running. I'd rather it just be killed so I can change the parameters and work it out. So interestingly, with Docker and with cgroups, you set the memory swap, but that is the total amount of memory that can be used by both resident memory and swap memory. So you just set it to the same as memory, and that essentially disables swap. Another quiz. What's going to happen now? Who thinks it's going to live? Good answer. So it's back to dead. Because now it's tried to use up more than 300 megabytes of memory, and then it's been killed. So right at the bottom there, we've got memory cgroup out of memory, and you can't really see the red on this, but it's basically saying, I've killed your Java process. It's not coming back. So of course, a lot of people know about this, that the JVM uses vast quantities of memory, which is not on our heap. The heap is just one small part of it. But if you're running a single JVM on a single server, and you're relying on ergonomics to kind of pick the sizes of various things, then you don't have to worry about it a huge amount, or at least for a lot of applications, you do not have to worry about it. But there are so many different things which can use memory in a JVM. If we think back to what I said about the default size, max size of a heap on a 64-bit Linux machine, it's a quarter of the available memory. Now, that could just be the JVM being super kind, or it could be a realistic expectation of how much of the memory should be allocated to heap versus other things. So certain things we're going to have a look at. We're going to have to look at how much memory our thread stacks use, how much memory does metaspace and the compiled code and garbage collection. And if you're using a framework which uses like direct byte buffers or any some unsafe memory allocation, that is off the heap. That is not going to get allocated. Ratpack, for instance, uses vastly more native memory than our drop wizard application does. So to see what's going on, and I just do this experimentally for each application, which I'm going to play with, you generally need this option, which is native memory tracking equals summary. You can ask for full native memory tracking, but apparently that's very expensive. So I just leave this one on all the time. Once we do this, we can use J commands to actually inspect what's using what memory for our running JVM. So I might give it loads of memory and make sure it's not killed, then jump on and start playing with it. So if you do a J command with no options, it's going to list you the processes, the JVM processes which are running. J command, for instance, is a Java process, a JVM process, so it's actually 166 up at the top there. But the drop wizard application we care about is PID25, and we are inside a bash running inside the container here, and that's because I often run Docker on hosts which don't have Java installed, so J command isn't there. Once we've got the PID, we can type J command PID and help, and it's going to tell us everything that JVM supports. So it's different depending on the version of the JVM. You'll get a bigger or shorter list. But we want vm.native memory. Once we run this for our drop wizard application, so to give you some context, I'm currently hitting this concurrently with 12 threads. So Apache Benchmark is configured to just make a very large number of requests as quickly as it can, 12 concurrent requests. So we can kind of see how our memory is divvied up. So because I've removed the constraints, it survives. You get to see the total amount. Oh, no. Don't do that. Apologies. So you get to see the total amount of memory used, which is the one I haven't circled, so committed memory. That's about 489 megabytes, which kind of goes hand in hand when we look to see that we'd set a limit of 300, but it was trying to use 180-ish of swap. But out of that, I do not want to use new presenter mode. No. Right. But if we actually look at what else is using up memory inside this JVM, one of the biggest for the drop wizard application. Now, drop wizard uses an embedded Jetty, which is very similar to using an embedded Tomcat if you've used Spring Boot. And For 12 concurrent requests, we've somehow created 102 threads, which seems an awful lot. So, and those 102 threads at the moment, and this was actually growing as I was playing with this, is using 104 megabytes of memory, which is a huge amount. Other interesting things that we've got in there are GC, that's reasonably large. We've got class, that's not too big, 27 megabytes. If you're using a framework or something which is using, say, direct byte buffers, you're going to see a really big section inside internal. I didn't actually know where things like direct byte buffers actually turned up inside this until I just allocated a big one and then checked. So let's say we want to try and work out how much memory we need for this. What we really need to do is tackle the biggest one first, or at least I think we do. So let's see if we can make the JVM use less memory inside this container by reducing the number of threads that it's going to use. So another really cool thing of jcommand is it will give you a thread dump. So you can signal a JVM process to do that, but that's going to stick it to the standard out of your JVM, which I don't know where that might be. If you use jcommand, it's going to print them all out. And I'm not sure if you can read it, but you can see virtually every thread on there is named nicely. So they're named things like dropwizard 71 and dropwizard 61 and DW 61, etc. So if we want to reduce the number of threads, because bearing in mind that I don't know what the default is for Jetty right now, but if we continue to hit it with more and more concurrent requests, if it continues to create more and more threads, it's eventually going to hit our 300 or 400 or 500 meg limit, and it's going to fall over in a heap. Whereas really we want it to service as many requests as it can and then stop accepting connections and to just service as many as it can rather than being saturated and overloaded and then falling over. So for our 12 concurrent requests, the dropwizard application, which think Jetty, let's wonder how many threads it's got. So all I've done is a jcommand, thread print, grep DW, and passed it into word count. So it happened to have 65 of those, which seemed a bit bonkers. But it's not the only thread pool which is running inside Jetty to service this. So it also has selector threads. So that thread that you get as an application developer to do your stuff on, the thing that's going to call into your REST controller, or if you're a raw servlet, it's just do get. Right? That's not actually the thread which is used to select data from NIO. There's a whole separate thread pool for that inside Jetty. And we found that thread pool. How many threads do we think we've got there? So that one was 24, which is kind of a suspicious number because this desktop had 12 cores. So the default for this, for selectors, is based on the number of cores, which if you've got a single JVM running on the host is a very sensible idea. But if we're running 100 JVMs, all with a few hundred megabytes of memory each, and we haven't even got to limiting CPU yet, then this is probably a very bad idea. Again, we've got acceptors. These are the things. These is a thread pool inside Jetty, which is actually accepting requests, so new connections. And that one came out as 12, which again was very, very suspicious. And this actually led to probably the funniest outage I've ever seen. So has anyone ever told you that you run your Docker container on your laptop and it works the same in production and it's immutable and all that wonderful things? Yeah. So we'd had an image which had not changed for months, right? However, someone was playing around with AWS instance sizes and decided, we can make this slightly more efficient. I'm going to flip to this instance size. And because we actually run a layer on top of Docker called Kubernetes as our container scheduler, teams shouldn't really care about that. We basically take one node out of the pool, we add another node, it has a different amount of RAM, and it has a different number of cores, and no one cares, right, because we're using Docker. So not a single one of the applications would start. And this is because Jetty tries to help you out, right? We'd already limited the number of threads which we're having as request threads inside dropwizard, right? Because we knew this was a tiny application, it has 5 concurrent requests, so we do not need more than 5 threads handling requests. But we hadn't actually overridden the number of acceptors and the number of selectors, right? And interestingly, Jetty tries to help you out. It basically says, if you're going to create 5 request threads, things which are actually executing your code, you probably don't want more acceptors and selectors, basically getting work off the network and giving it to them, because that would just be a little bit silly. But if you happen to have overridden and hard-coded your number of request threads and not your selectors and acceptors, Jetty just says, no, I'm not going to start, illegal argument exception. So that nice immutable image, yeah, not so much. So of course you can override this. So we started off talking about JVM ergonomics and how the JVM itself is very much geared to tuning itself based on the amount of memory and the number of cores on a particular host, so you don't have to. But it doesn't stop there. We've got virtually every library and framework that has a thread pool. Most of them will not hard code a number of threads. They will normally base it off, say, the number of cores. So we need to override these two as well, which we learned badly. But that doesn't help us with the fact that a thread is extremely expensive. Now remember that even if we kept it down, even if we actually wanted to handle hundreds and hundreds of concurrent requests, now we seem to have got in the habit of building lots of services which call out to lots of other services. Right? We call out to databases, queuing systems, loads of HTTP services. You know, these are typically like blocking I/O calls. So we're making a HTTP request with our favorite Java HTTP client. And most of these in the Java world happen to be blocking. So if we want our Drop Wizard application to handle 1,000 concurrent requests, it does actually have to have 1,000 threads. And each of the stacks of those threads is going to use up about 1 megabyte. We can try and reduce the stack size in Java and try and get it less than that. But it's a huge amount of memory just for some threads that really all they do is sit around and wait for your friend's service to respond to you. So what's the solution? Node.js. I think we can get away from this whole using threading, operating system threads as our abstraction for concurrency, and we should definitely all know. So there are loads of really cool examples of frameworks and tools in Java which do not do this. Most of them for networking frameworks are built on top of Netty, which is awesome. The one which we use in my current company is Ratpack, which is a steep learning curve if you haven't done a lot of, say, functional programming or dealt with asynchronous frameworks, but it's worth it if you've got a high throughput service which is going to make calls out to other ones. I've used a lot of Akka in the past, but Akka tends to take over most of your application, so we didn't use that at the time. So the benefit of these frameworks, and this isn't a talk on asynchronous programming or non-blocking programming, is as soon as you go to make an external call out, that thread goes back to servicing a different request. So we have applications which would have 4 compute threads, so 4 Ratpack threads, 4 actual request threads that can handle hundreds and thousands of concurrent connections. So that's the benefit. But just because we've done that, it doesn't mean that we get to say, hey, we don't need to do any configuration now. Because pretty much every one of these frameworks, libraries, tools that I've used, they all, again, base their number of threads off the cores on the box. I mean, these frameworks are often called thread per core. Because, there's no point, when your thread, when it's blocked on I/O, doesn't just sit there, it's actually used for something else, then having more threads than cores is a bit silly, because they'd just be contending and context switching. Where in reality, you just want to use one thread on one core doing as much as it can. So the problem is less, because the Ratpack, for instance, that only ended up with 24. Not the hundreds we were talking about with Drop Wizard. And its default, by the looks of it, and I didn't actually verify this, was double the number of cores. I guess you can block 12 of them. An interesting thing to note is when I did the exact same load through this Ratpack application, and we fire up cgroup top, it doesn't really use much CPU, or certainly by this accounting statistic, because really the Ratpack threads, they call out to another service and they're just sitting there doing nothing. But even if we've solved all of our frameworks problems, we do need to address ourselves and go back and have a look at the JVM. So we have lots of awesome concurrent garbage collectors, right? But how many threads do you think they make? Okay, they're going to have a look at the number of cores they want to get through your heap as quickly as possible while they're doing a concurrent sweep. So that, again, is based off the number of cores plus a couple. What we essentially need to do is rebuild JVM and ergonomics, but base it off the amount of resources we've given to Docker, not on the amount of resources on that host. Or in reality, I wish Oracle would just make the JVM cgroup aware. There's also compiler threads. So this is the thing which actually decides, the JIT says, hey, that's a hot bit of code, I'm going to compile it. That, again, is based off the number of cores. That doesn't get very big. You have to end up with a lot of cores before you get to a big number there, because it's not like a one-for-one mapping. But again, we probably don't need 4 of those if we're going to give this container 128 megabytes of memory and half a core or a couple of cores. Thread pools inside our frameworks. So a lot of people, I'm guessing, have played with parallel streams, or they've played with the completable future, and they've asynchronously transformed values inside futures. You're not getting computation for free there. It ends up on the default fork join pool. And how many threads do you think that has? It's based off the number of cores. And again, a lot of frameworks just use that as an option. So you really need to take a regular thread dump and actually work out, which ones do I actually need to configure. And it's super easy to miss one or two. So even though I've spent the last 10, 15 minutes talking about threads, I still haven't actually gotten to how we limit CPU inside a Docker container. I think we're quite used to, as Java developers, dealing with garbage collection pauses and maybe some OS pauses. But when we run our JVM inside a Docker container, we try to break up the CPU on a host and share it amongst many containers. They actually behave quite differently. The way they're given time on the CPU is different. So if I take our good old drop wizard application and I start hammering it with 12 concurrent requests, we can use cgroup top to see that it's got 731% CPU. So it's using over 7 cores. And we can verify that in top, and we can see it's 700-ish right now. Now that sounds like a great idea if we had a single container or maybe 2 containers running on there. What we need to do is equally share, or at least be able to decide which process gets the priority. And this is where I've got a bunch of Docker Compose files for. So we have 3 tools to be able to do this, and each of them will make your JVM, your application, behave kind of differently. So the brute force tool is something called a CPU set. So that allows you to say this process, the processes inside this Docker container can only run on these CPUs. And it's just numbered based. So on the machine I ran this stuff, it has CPUs 0 to 11. I gave the wiremock application, which is the application which the drop wizard and the Ratpack application call out to. I just gave that loads of CPUs because I didn't really care about that one. And then I decided that my Ratpack application and my drop wizard application could have 1 core each. So once we boot up the containers with that configuration, what we get is a perfect 100. And we can still see that the wiremock process, even though we gave it 4 cores, it's actually only used 22% CPU. Whereas the drop wizard application, which is getting hammered, and really the wiremock one too, but it doesn't use as much CPU, is pinned to 100%. It's using as much as it can. But we could have many different JVMs using a core each, and they wouldn't necessarily overwrite each other and contend with each other. But that is a very flaky way to do it in my experience. Like good old Chris changing the number of instances. If you somehow decided that I had less instances and you'd pin particular JVMs and particular containers to particular cores and they didn't exist anymore, that'd be pretty bad. So what you're typically using are 2 modes. And it's whether you want the actual JVM to be burstable or not. Because you can take 2 approaches to limiting CPU or Docker containers. You can either say, I want this thing to have 1 core. And it's always going to have 1 core, and it is never, ever going to use more than 1 core. But if we think about why we've started in this journey, it was to increase utilization. So what happens if we had 12 applications running on 12 cores, and 10 of them were having a nap? They didn't really care. Do you want the other 2 JVMs to be able to utilize the rest of the CPUs in that time? If you do, what you probably want is to use CPU shares. So looks like a big fancy number. It's really just a relative weight of how much CPU they're going to get. By default, if you don't specify anything, a container is going to get 1024. So that's why I always have that as basically 1. But we see we've given wiremock 4 times the amount of CPU share than we've given, say, the Ratpack application and the drop wizard application. But if we run our benchmark again, because CPU shares essentially anything which isn't used goes into a global pool, which then any container can use, we can see, and you'll have to believe me, the drop wizard application is the 3rd value down. So when we use cgroup top, we can see / and then we can see Docker, how much are all the Docker containers using, then the 3rd one down, which is 676. So even though we've limited it to what we think is a quarter of the CPU as the wiremock application, it's still using 6, nearly 7 cores. And to think about this can lead to some pretty funky behavior if everyone does decide to use their CPU shares. So imagine my very hypothetical example where I've got one container, one JVM, and I happen to give that 1024, and I've got two other less important JVMs, maybe they're Jenkins slaves, and I give them 512, so they're green containers. If I happen to land on a host which has two cores, kind of roughly, the yellow container is going to get a core to itself, whereas the green containers, they're going to have to share a core. They're really not going to get enough CPU time to service requests. However, if we happen to land on a machine with 4 cores, then yeah, the yellow one's going to get 2 cores, and the 2 green ones will just get a single core. At my workplace, we use CPU shares a lot for our Jenkins slaves. Because if all the builds are running all at the same time because we've got super productive developers, then what happens is they get an equal amount of CPU each and they'll go equally as slowly. But if some guy stays late because he's keen and he commits a load of stuff, he gets to use all of the host resources because it will burst past its actual shares. But if you come to do capacity planning and you come to start load testing your Java applications and you're using CPU shares, what tends to happen is you happen to run your test, your load test, and maybe something's running on the host, maybe it's not. This is the whole point of Linux containers and schedulers, is you're not really sure where you're going to end up. Then you might get to use the whole core, and you might be on a 64-core box, and you might be having a great time. You basically say, I'm only really using one core. I think I'm using one core, and I can service thousands of requests a second. I'm amazing. But then you come to production and you've got some multi-tenancy, or you rerun the same test and there's a bunch of other things running on it, it'll go much slower. So what you can use if you care about that kind of stuff and you want to do good capacity planning is you can use CPU quota instead. Now just to remind you, this is a feature of control groups. You can access it via Docker, but if you come to use a different Linux container engine, say Rocket, all of the knowledge you learn about this stuff is going to be the same. Or if you're using systemd and you're giving things quotas via systemd, you can do that as well. And this one is slightly different, so forget about the relative weights now. What you get is a certain amount of CPU quota per period. What that really means is the default period for Docker, which you can override, is 100,000 microseconds. So what that means is if you want a whole core, you can also say what you really want is 100,000 microseconds of CPU time every 100,000 microseconds. And that basically means that you get one core. If you want 2 cores or something equivalent to 2 cores, then you could say I want 200,000 microseconds of CPU time every 100,000 microseconds. And because you can't travel in time or anything, that means that the only way you could get that quota is to have two CPUs available. So in this example here, we've set essentially that the WireMock gets 400,000, a quota of 400,000 every 100,000 microseconds. It's like 4 cores. And then we've just given the Ratpack and the Drop Wizard application 1 each. So it's similar-ish to the CPU sets example, except it doesn't matter which CPU we end up on now. It might not even be the same one. And if we run this now again, and that's our Drop Wizard application sitting in the middle there, we've got it at 107% CPU. Now remember before, without any limitations or with shares, it shot up to like 700%. When we did CPU pinning, it went on exactly 1 core and it was 100%. But when it comes to quotas, you'll see it go up and down and sit around its quota if it's trying to use it a lot. I'm not sure if that, in this example, it's because of the way this reports CPU usage time. But you'll generally find that what happens is if you use up all your quota because you're getting cool user requests, and then you run out of quota, what the kernel will do is pull your process off. You'll be throttled. So any outstanding user requests that you've got coming into your amazing Java application, they will not get any CPU time. And there'll be another blip inside for your application response time. You can get some funky distributions in your latencies. And cgroups actually expose a metric for how often that happens. And you can grab that metric with the tool I'm about to show you, send it off to like a central graphing tool. If you're running your load test or in production, you're like, why on earth do like 20% of my requests take over 500 milliseconds, or they all come in 20 milliseconds? You can see how many times you were throttled due to Docker, due to running inside a cgroup. If you don't like lots of tools which I've showed you and you like nice pretty things, then I definitely suggest running cAdvisor on every single host that you're running your applications on. It's a tool by Google. It can actually run as a Docker container, which is crazy. And what it really does is it reads that file system that we looked at right at the start of the talk and gives you all the information in a nice web UI. So right away, if you're a Docker container, you can see the number of CPU shares, whether it's on a CPU set, whether it's pinned to a particular core, what its memory limit is, etc. And it doesn't just offer you a pretty UI. It actually exposes all of these metrics over HTTP so you can grab them and shove them in a central metrics database like Prometheus. And we found that absolutely so unbelievably important to be able to do, because what you'll actually want to see is how much CPU is my container, my Java application using across everywhere it's deployed. And that's very hard to do with typical tools, but with this plus Prometheus or whatever metrics database you tend to use, it's really good. It's really easy. So that's about it. The kind of takeaways, if you fell asleep because I was boring, is if you're going to run a JVM inside a container, learn a bit about how control groups and namespaces work under the covers, because it will be invaluable. And then do a bit of extra capacity planning around checking how many threads every part of your application uses, and make sure it's relative to how much memory you're giving that container. And what you end up doing is creating a shell script which starts your Java application, which looks a lot like a Java ergonomics. And for memory, you just really need to experiment and test. So on that note, thank you very much for listening, and it was a pleasure.